Okay, so we're back, and what we're going to try to do today is really talk about the rest of Turing machines and really try to make it a little bit more formal than what we did the last video. So in that last video, what we did is we went through this kind of seemingly simple example and used that example to motivate what a Turing machine is and to kind of illustrate the differences between a Turing machine, its inner workings, and all of the other types of machines that we've talked about in the semester. And so the closest to a Turing machine would be a push-down automata. And we saw in the last video that while push-down automata are very similar to Turing machines, there's some key differences. And we sort of used that example to kind of walk through what those key differences are. So just to recap that, the push-down automata typically has an input tape and also a stack, and these things are managed separately. Turing machines actually kind of combine those two ideas, and not only can you push and pop things off of the stack, you can actually move left and right along the entire tape that the Turing machine has as both its kind of internal memory and its input. So what we're going to do now is we're going to talk about the actual mathematical definition of what a Turing machine is. And in that discussion, we're going to point out some differences between what we went over in the last video and what the textbook has listed as the sort of mathematical rigorous definition that they provide. And we're also going to use that as a segue to talk about Turing's thesis, which is maybe top three most important things in the course. And so we've talked previously about how certain things are really important. One of those things being the pumping lemma was extremely important. One of those things being the equivalence of DFAs and NFAs, that's extremely important. The concept of language families, extremely important. Turing's thesis is among the very most important of those important concepts. And we're going to quickly go through what it kind of means and its motivation in this video. So I'm going to start off with the formal definition of what the heck a Turing machine actually is. And so if you look in the definition in the book, it's going to slightly deviate from what I'm going to show here. And I'm actually going to explain briefly why their definition is slightly different from mine and why it doesn't actually matter. So how we're going to define a Turing machine is a 6-tuple of the form, looks very similar to all the machines that we've talked about previously. Looks kind of like a DFA, NFA, looks kind of like a PDA. And you may recognize some of these symbols, and you can probably already in your mind think of what those symbols actually represent. So Q, exactly like we've seen it everywhere else in the class. This thing is going to be a set of internal states. Those internal states are effectively going to represent the control unit itself. So whatever the current state of the control unit is an element of Q, which is the set of internal states for that control unit. Then we have sigma, which is the input alphabet. This is the same concept of an alphabet that we've used throughout the class. And so we're using the very kind of familiar symbology to represent it. Gamma is the tape alphabet. So if you remember the lecture about push-down automata, the exact same concept. We have a tape alphabet, we have an input alphabet, and all of the things that can be represented on the tape don't necessarily appear in the input alphabet, and we're going to talk about that in detail in just a moment. Next, we also have a transition function. Again, the exact same concept of the transition function as we have talked about it from the very beginning, maybe week 2 of the course. This is a transition function that effectively takes you from a current configuration in the Turing machine at time t to the next configuration of the Turing machine at time t+1. And so if you look back at the previous video, you can see kind of how we did that with the example last time. So again, familiar, Q0 is going to represent the initial state, and then F is going to be a subset of states that exist in Q, but these are going to be marked as accepting states. And so these states inside of F are states where if we terminate the computation inside of one of these states or at one of these states, we will accept the computation as part of the language or whatever our definition of accept means for the particular problem we're trying to compute. So just a couple of notes. So the first note is that the textbook itself actually represents a Turing machine as a 7-tuple and includes the symbol that they choose to be what we call the space or the special character at the end of the input last time. Personally, I think that is not super great. We shouldn't necessarily include that symbol as part of the design of the machine. That's really more an assumption. And so baked into our definition is the assumption that we have some special symbol that is not in sigma, our input alphabet, but is in gamma, the tape alphabet, that we can use to understand when an input has been consumed. The reason why I don't like to necessarily use that as part of the definition is what we're really trying to get to is a generalized machine that can do whatever computations it wants. The only real reason why we need this special symbol is because we need to understand what being done with a computation actually means. And so colloquially, we've used the idea of consuming all of the input to be the marker that indicates, hey, our computation is done. That is not necessarily a requirement for all Turing machines ever. That's just kind of a special thing that we've adopted in our course or in our study of the field. So while they call it in the textbook a 7-tuple, I call it a 6-tuple. If you look at the textbook's definition, they're going to have a square here somewhere around the Q0 or the F. I've removed it, and the reason I've removed it is I have simply added it as an assumption that we have our upside down cup, or our cup, not an upside down cup, but the squared out cup here symbolizing our space, and that symbol cannot be inside of the input alphabet. The second one is that in the previous lecture, we had an entire slide that was dedicated to the idea that specific behavior exists for Turing machines to determine when a computation has been accepted or rejected. And what we said on that slide is that there are usually special states, so we can call them Q sub A for accepting or Q sub R for rejecting states that are inside of Q that indicate that once that state is reached, regardless of what happens on the input, we terminate computation and we either accept or we terminate. I want to be very clear that this definition does not preclude what we outlined in that slide. Indeed, both of these things can be true at the same time. What this definition is letting us do is it's letting us generalize the idea of a Turing machine to the point that we can have either a Turing machine that is an acceptor or a Turing machine that is a transducer, and both of those types of Turing machines have the same mathematical definition. So what this definition is saying is that I can have a set F of accepting states that's inside of Q. Previously, what we were effectively saying is that there is an F that has exactly one element, and that one element is the accepting state. And then we also effectively added some transition rules that said as soon as I get to a specific state that is not an element of F, I should terminate. And so I would not have any rules that allowed me to get out of that state and into another one. And so we talked about last time how the rejecting state and a trap state are extremely similar, and that's how it would be implemented. One of these reject states would effectively be a state that you would always be trapped in because you would not be able to leave it via the transition function. So I wanted to be very clear that this definition is effectively a generalization of the things we were talking about last time, and really the reason why we make that generalization is because now we can talk about either acceptors or transducers, and we don't have to necessarily change the definition of what a Turing machine is to do so. So the hard part, or the more complicated part of all of these machines that we've been talking about recently, have really been about the transition function. That's where most of the complexity is. And so if we remember what the transition function for PDA looks like, it looked kind of ridiculous, and from a mathematical perspective, the transition function for a Turing machine also looks kind of ridiculous. So we have some function that is taking us from the Cartesian product of our states and our tape alphabet, and it is taking us to the product of that same space with a set of moves, effectively. So an L or an R indicating that we can go left or right with the read-write head after updating the state and then changing a specific character on the tape. So the obvious question when you see this is what does any of this actually mean? And so basically what it boils down to is that if you want to put input on the tape to begin with, we know that the symbols that represent that input have to also be on the tape alphabet, because if you had symbols that were in your original string that weren't on the tape alphabet, that means that you wouldn't be able to represent your input string on the tape alphabet. And note that we know that the input alphabet is a proper subset of the tape alphabet, because we know we have at least that one special character, the space character, that can't exist inside of sigma. So what's happening is the reason why you don't see sigma in the domain or the range of this function is that gamma contains sigma, and that's basically what this is trying to say. And so what we're trying to do here is we're going from one of those configurations that we talked about in our example last time, some state in the control unit, some current string on the tape, and we're trying to go to a new configuration that is marked by a specific new state in the control unit, be it the same one or a different one, and a different string that is represented by changing or leaving the character that the read-write head was pointed to, and then an update to that read-write head, either going to the next character to the left or to the right 1 unit. So it is absolutely true that you can represent the transition function of the Turing machine as a transition graph. And what we could do is we could go back to the slides from the last video, and we could update those slides, and instead of using kind of words to represent what the states actually meant, we could draw a finite state machine. And that finite state machine would be the visual representation of the transition function as a transition graph. And that should be fairly straightforward to do, given that there are kind of a finite number of states and the finite number is fairly small. But as you saw on the midterm, and as you've seen on many of the homeworks, trying to derive a finite state machine is not particularly easy for a lot of different cases. And as we saw with PDAs, when you try to build a finite state machine that is also decoupled from your memory management system, so it's decoupled from the stack, or in this case, the tape, and it's also decoupled from the algorithm in our case that we're trying to implement, that can be kind of difficult to wade through. So instead, what you often see are these rules that effectively take a configuration in, and then as output, they provide to you what the new configuration would be. So if you look at this kind of mathematical representation of such a rule, in English, what this is saying is that I am currently in state Q0, and I see an A underneath the read-write head. One of the legal things that I can do is remain in Q0, the state. I can replace that A with a B, and then I can move the read-write head to the right 1 slot. And so this kind of makes sense. It's very clear what you can and what you cannot do. If you have a whole huge list of rules, you can quickly search through those rules and determine what's a legal move and what's not a legal move. The problem is it is entirely up to you to keep track of the current state of the tape. And if you miss anything about the current state of the tape, you can kind of go off the rails, and you could potentially be making moves that are illegal because you have not correctly updated the state of the tape. And so as a human, it's fairly difficult to do all of this kind of bookkeeping yourself. And so what we really need is an intermediate representation of these configurations that kind of makes the current state of the tape explicit, so that you can more clearly walk through algorithms and spend your time debugging or actually deriving algorithms rather than doing the sort of mechanical walking through step by step and making sure that the algorithm is even well posed. So that brings us to turnstile notation once more. So we did a couple of examples of this in the PDA's lecture, and it's going to look fairly familiar to you if you've been through those lecture slides. If you are confused, if you missed the class, if you have never seen this notation before, you can actually go back into lecture slide set number 17. If you go to that lecture slide, there is an example that walks you through a step-by-step example of how the rules on the previous slide kind of match up with this kind of notation. The good news about this is that while the PDA turnstile notation is fairly straightforward and it kind of makes sense, the notation for Turing machines is even more straightforward, and at least in my mind is way more preferable to the PDA version. So just to get the kind of notation out of the way, that notation looks exactly like this. So it is significantly more verbose than just the rules that represent the transition function itself. But what's happening here is we are representing not only the rule that was taken in the algorithm, but we're also representing how that rule's application changed the current state of the information on the tape. So if we look at this, we have three main pieces here. We have terminal symbols that are on the tape. We have a state, which acts also as the read-write head. And then we have the entire thing together separated by this turnstile symbol. And so what this means is that everything on the left through a transition became everything on the right. And so, as you can see, this Q0 also acts as the read-write head. So the character immediately to the right of the state is the character that is currently pointed to by the head. And so what this means in English is that I started in state Q0, I was reading an A, I had not read anything else potentially, and after my update, I remained in Q0. So on the right-hand side of the turnstile, I'm still in Q0, but I updated my A to be an X, and then I moved my Q0, my read-write head, to the right one slot. And so you can see that this notation effectively gives you all of the information about the update or the rule that you applied, but it also tells you a whole lot more information about the state of the tape. And so you yourself don't have to have scratch paper laying around somewhere trying to keep track of what each individual letter means, because that information is already encoded inside of this intermediate representation. So what I want to do really quickly is go through our previous example from the last video in turnstile notation. We're going to talk a little bit about how algorithms themselves are related to Turing machines at the very, very end of this video. But basically what we want to do is we want to go through one example of using our previous algorithm to kind of represent or show what that algorithm's implementation looks like inside of turnstile notation. So the language that we were interested in that example was the language that is just two strings that are some collection of zeros and ones separated by a hash sign. So the same agglomeration of zeros and ones should appear on the left and on the right of that hash sign in order to be a string in the language. So if you were to give me a string, the algorithm that we developed is an algorithm to figure out if the string is in the language or not. And so what we're doing here is we're building an acceptor. We are answering the membership question for this language. And in turnstile notation, the first couple of steps of that algorithm look something like this right here. And so just to briefly kind of recap the idea of what the algorithm is doing, what we're going to do is we're going to start at the very leftmost character. We're going to use an internal state to understand what that character was. We're going to seek to the right until we see the hash sign. Then we're going to check the sign to, or the symbol to the right of it. And because we have encoded what we previously saw as a state, we can use another transition to understand if this character matches with the first character, and if it does, we can continue the computation. If it doesn't, then we know that we can stop and reject the string because the string can't be in the language. And so if you look at the turnstile notation, that's exactly what we're doing, right? So we started at some Q0, we were pointed at the very leftmost character, we read that character, and as part of reading that character, we updated from Q0 to Q1. We marked off that character so that we know where to come back to after we process the match on the right-hand side of the hash sign, and then that's our first update. So we initially were in Q0, we were reading a 1. Now I'm in Q1, I've updated that 1 to an X, and I've moved my read-write head to the right 1 so that instead of a 1, I'm now reading a 0. So next, we are going to seek to the right until we find this hash sign, and then we're going to seek right one more time and read whatever is to the right of that symbol. And so just like we've done with productions in the past, and just like we did with turnstile notation for PDAs, we have this clean star or this superscript asterisk here. And what that means is that I have done multiple moves here, but none of them are really interesting. So what this means is I have taken Q1 and I have made no changes to the input tape at all. And what I've done is I've just moved right a certain number of times. And so I've been able to move right 1, 2, 3 times. And at the end of that, I've got this intermediate representation. I use this because otherwise I'm going to have a whole bunch of trivial intermediate steps in here that are just going to confuse matters even more. So instead of confusing things and making it really verbose, I can just use shortcut notation with a clean star. So the next interesting kind of move or update I can make is I can check to see if this 1 matches the very first character that I looked at. And so we talked last time about how we do that with internal states in the control unit. So the next step, I'm actually going to recognize that I've read a 1. I'm going to update that 1 to an X, but I'm going to move myself into Q2, state Q2. And so what this means is that Q0 effectively means that I'm ready to match. I haven't necessarily read anything at all. In step Q1 or in state Q1, I've seen an unmatched 1, and then in state Q2, I have seen a match, and now I know that I don't need to terminate the computation in a reject. I'm on the path toward acceptance, and now all I need to do is seek back to the beginning of the string and effectively apply the same idea over and over and over again. And so if I do that, it's going to look something like this. And so the next time I rewind, I'm going to go all the way back until I see an X. Note that I've used the same clean star notation here. What this means is I'm effectively rewinding Q2 all the way to the beginning. And I have updated my state to Q0. The reason is because I want to be ready to match again. I want to be able to understand what the very next symbol on the left is and appropriately match that thing. And so after I've rewound, I'm going to turn the 0 that I find into an X. I'm going to update my Q0 to a Q3, which we were saying means I've seen an unmatched 0. and then I'm going to move my Q3 or my read-write head to the right 1. So then what I'm going to do is I'm going to fast forward on the tape until I reach the very next symbol. I'm going to recognize that that 0 is matching to my previous 0. I'm going to update to Q2 after I read it. That Q2 means I've seen a match. It doesn't matter if it was a matched 1 or a matched 0. I don't actually care. And at this point, I know that I matched my 2 zeros. I'm in Q2, state Q2. So all I need to do is rewind to the very beginning and continue about my life. And so these last 2 steps are, again, clean stars or shortcut notation for showing you what the last 2 steps of the algorithm look like. I go back to the beginning, I'm pointed to a 1, I update to state Q1, then I fast forward, I recognize that I have a 1, I consume that 1, and so here this should actually be Q2 for seeing a match, not Q3. So at the end of the day, what should happen is I should be in this state, except this should be a Q2, and then everybody's happy and the computation is done. So what I want to get across is that while if you just picked up a book and you had never been shown turnstile notation, if you had no idea what it actually meant, and you looked at this computation in a random page in a random computer theory book that you picked up at the library, you might be extremely weirded out by the symbology. It looks a little bit like some runes or something, but really when you break it down, all it means is that we have a transition function that has some rules, and we can apply those rules to the state of the tape. And in doing so, we can arrive at some configuration, and we can, as part of our algorithm, determine if that configuration is valid, if we're going to accept that configuration, or if that configuration is invalid and we're not going to accept the computation. So the good part about this is, even though it looks kind of mysterious, it allows us to very succinctly discuss the computation, and it allows us to provide examples of our algorithm working without us trying to hand draw dozens and dozens and dozens of machines and sort of screenshots of machines at specific points in time. This is a much more succinct way to kind of have intuition about algorithms without doing a bunch of drawing. So this is very similar almost to the difference between a regular expression and a DFA. If you want to have a conversation about an algorithm, this is a way better way to do it than trying to draw a Turing machine. The interesting thing about it, though, is if you have some intuition about the algorithm itself, this also illustrates that you can actually build the finite state machine that represents the control structure by stepping through some computations and using examples to kind of build the machine sort of going in reverse. So if you were in a situation where you had to build a Turing machine as a design for some sort of machine, you would be able to do that with this turnstile notation using some examples to kind of drive your design. And so that's another really good use for turnstile notation. If you're not necessarily trying to communicate with about an algorithm, you're trying to build the machine, this is a good way of kind of reverse engineering what the finite state machine for the control unit should look like. So the next thing we're going to talk about is what the concept of a standard Turing machine is. And it turns out that there are a whole bunch of different definitions. And at FSU, we use this book that we've chosen for the undergraduate class by Peter Lenz. There's also the graduate course that we teach usually out of the Michael Sipser book. And even in those 2 books, out of dozens and dozens and hundreds of books that have been written about automata theory, there are differences in how they derive what a standard Turing machine is. And this is all kind of predicated on the idea that the textbook and I can have a disagreement about what the mathematical definition of a Turing machine is. And ultimately, what we actually care about is that me and the textbook and whatever textbook you're looking at and whatever Google search result you found about Turing machines, as long as we are talking about a set of machines that has the same computing power, that we haven't added something or subtracted something that actually has a demonstrable impact on its ability to compute things, everything kind of washes out in the end, and everything is kind of the same. So one really good example of a difference in standard Turing machine definitions is that the textbook actually indicates that the tape on both ends has to be infinite. And if you watch the previous video, if you go back and you look, I actually said that the left-hand side had to have a boundary. So the tape itself only needed to be infinite on one side. But it turns out that it doesn't actually matter. Both of those configurations of a Turing machine are equivalent. And if you kind of want to reason around why they could be equivalent, think about what would happen if we took my Turing machine, it's bounded on the left end of the tape, and we picked the input up and we shifted it to the right by some arbitrarily large, maybe even infinite number of spots. What will happen is now we suddenly have the exact same input on my machine that locally looks exactly like the machine that the textbook is explaining. And note that we don't actually have to modify my machine at all in order to make that conversion. And in fact, the algorithm that we used to solve the example in the previous video would still work. It would need some minor tweaks, but the tweaks would be to the algorithm itself and not necessarily the machine that we used to implement that algorithm. So just by shifting the input, we can make the machines equivalent, and by changing the transition function slightly, we can compute that exact same example, and in fact we can compute whatever example a version of the textbook's version of a Turing machine wants to compute. So now that we've kind of gone through the mathematical definition and we've kind of gone through this kind of colloquial discussion about how everybody in the world can disagree about what the standard Turing machine actually is, as long as the disagreements are about things that are not of consequence, what we want to do is do a more complex example of building an algorithm on a Turing machine and actually computing something that on one hand seems really, really trivial, and when you try to start doing it with something like a DFA, it will become significantly less trivial as you try to accomplish it. So the task that we're going to try to tackle here is building an acceptor for a language that is represented by a series of A's, a series of B's, and a series of C's, but the number of C's that I have in any string must be the same as the number of A's times the number of B's. And so if you were given a question or given a task like this on a test, or if you were given a task like this at your job or for whatever reason, the first thing that you might ask yourself is, can we do this with a DFA? And it turns out that no, you absolutely cannot do this with a DFA. Can you do this with a PDA? The answer to that is I don't actually know. Maybe you could. I haven't really spent a lot of time trying to do it, and that's not really near the top of the list of things that I want to necessarily do. But you can certainly accomplish this task with a Turing machine. And so this is a very clear example of a computation that we can do with a Turing machine that we cannot necessarily do with a DFA. And even though it's just an acceptor, it's just answering the membership question for a specific language, it is a non-trivial language in that in order to solve the membership question, you also have to actually perform arithmetic. It isn't necessarily a case of just simple counting, or it is a case of simple counting, but it's slightly more advanced than the sort of simple counting questions that we've done in the past. So I have thrown away the control unit in this case because, as we just showed, really the intermediate states, as long as we can make an argument that the states exist, that's really all we need. And those states do little more than actually remember what we've done. So the states themselves don't actually matter all of that much. You can derive the states if you want to actually go through the intermediate representation of the algorithmic steps to solve the problem. But I kind of leave that to the reader as I need the screen space, to be honest. So what we're going to do is we're going to derive an algorithm that allows us to understand if this string that is on our input tape belongs to this language or not. And like with the previous example, that algorithm, it turns out, is going to be able to work for whatever string you want. We're just using this example to kind of motivate the design of what the algorithm should look like. So we can kind of check ourselves here to make sure that this is a string that should be accepted. So we've got 3 A's, we've got 2 B's, 3 times 2 should be 6, and we've got 1, 2, 3, 4, 5, 6 C's, so this thing should be accepted by the acceptor. So the interesting thing about algorithm design on a Turing machine is that basically the first question that you should ask yourself about any of these questions should be the most primitive question you could possibly imagine. Like we talked about last time, programming an algorithm on a Turing machine is very, very, very similar to programming something in assembly, or even maybe probably closer to machine language. And so the first question we want to ask ourselves is, what is multiplication even? What does it actually mean in context of this problem? And so what it actually means here is we want to understand the number of C's, and we want to be able to verify that the number of C's is equal to exactly A groups of B things. So the idea then is going to be to mark off each of these groups, make sure that we have at least that number of C's, and then proceed through each of the groups, making sure that A, we don't terminate early, and B, after we are done matching all the groups, we don't have excess input on the tape. So to go all the way back to one of the very first slides in the presentation for this video, this is one of the reasons why we need the space, right? So if we didn't have the space, we wouldn't necessarily understand where our input stopped. And where our input stops is going to allow us to understand if we have excess stuff on the tape, which means that we have excess C's that we can't match to a group of B's. So let's figure it out. So the first thing we're going to do is we're going to mark an A. Then we're going to step all the way through those A's and find the first B, and then we're going to mark that. Then we're going to find the first C, and we're going to mark that dude. But we're going to go backward and find the next B, mark it, and then mark a corresponding C. And this is effectively one iteration of the algorithm. We have an A, and then we're going to try to match all of the B's that correspond to that A to some group of C's. And we're going to try to do that until we run out of input. And if we have unmatched things, we're going to reject. If we have excess things, we're going to reject. So this time what we're going to do is we're going to go back all the way to the A's because we don't have any B's left. And we're going to mark the next A. The problem now is that we don't have any B's to mark with. And so what we're going to have to do is unmark those Y's, turn them back into B's, and go through the process again. So we're going to unmark the B's, then go back to the beginning of the B's, mark each of the B's off with a C, a corresponding C, and then go all the way back to this A, and do the same thing. Unmark the B's, mark a B for each C for the corresponding A. You note here we're processing the second A, so that's going to correspond to 2 additional C's being marked off for each of these B's. Then we're going to go back to this A, unmark these B's. We're going to have 2 additional B's for this third A, and that's going to correspond to this C and this C. So after some number of computations, what I'm ultimately going to result with, or end with, is a whole bunch of X's, a whole bunch of Y's, a whole bunch of Z's, and then suddenly I'm going to see the special character that we denote as space, or effectively nothing, at the end of the input string. And so when I hit that special character, all I need to do is go back through the tape and look for any A's, any B's, and any C's. And if I find any A's, B's, or C's, then I have to reject, because I recognize that I had some A's or B's that I did not match with a C, and that can't be allowed in any string that's in the language. Additionally, if at any point I prematurely hit this special character, so if while processing a B I hit the special character, I would also know that I need to go to the reject state, because I don't have enough C's in order to be a string that's inside of the language. So if we go back through and we only find X's, Y's, and Z's, that's the only case in which we can actually go to the accept state. So in that case, we've actually seen a string that has the correct number of A's, the correct number of B's, and the correct number of C's, and we know that we can answer the membership question with a big yes. So a sort of, I'm going to call it homework in quotes for you to do would be to write down the turnstile notation for this computation that we just went through. And what that will do is it will require you to struggle through that notation and kind of understand what the heck the algorithm is for this particular problem, but also what the notation actually looks like. And if you can struggle through that notation, it will be very illustrative to you. And a lot of the information that we've covered in this lecture is going to kind of just click all at once. That's how this stuff typically works. If you have trouble trying to derive the turnstile notation, please send me an email, or next week I'll start having digital office hours online, and we can kind of go through it together. It is a very, very important sort of exercise to go through on your own, just to make sure that you understand the notation, because as we go through these Turing machine lectures, that notation is going to get used over and over and over again, and being familiar with it is kind of the first step to success there. So the next thing in the text is section 9.2. It's a very short section about combining Turing machines. And the idea here is you can combine Turing machines to do really complex calculations if you want to. You can build one Turing machine that's an adder, you can build another Turing machine that's a multiplier, and you can combine all those things together to the point that you have effectively a calculator of Turing machines. I'm not going to belabor the point about combining Turing machines because it should be fairly obvious that you can do so. And in fact, we've combined machines in the past when we talked about how to show that a language is regular by composing DFAs and NFAs together using lambda transitions or whatever transitions you want. The reason why we went through those kind of pedantic exercises of showing things like the complex numbers are regular languages is that it's a much easier way to prove the same point that this section of the book is trying to show. And that's that if you can show that you can compose these machines, it is much easier to solve problems or show things are regular or show things are an element of a specific language, for example, by sort of divide and conquering the problem. And so that's exactly what you can do with a Turing machine. So what I would do is if you're a studious person, I would look over section 9.2 at your own leisure. It is very, very short. It does not take a lot of effort in order to get through. The high point of it is that it doesn't actually matter if you use the textbook's definition or my definition of a standard Turing machine. there isn't a special input file in either of those definitions. And so just like we had lambda transitions between NFAs that built a larger NFA, you can have a Turing machine that starts with some input on its tape, and then the output of that machine can exist on the same tape that is then read by Turing machine 2. And the output of Turing machine 2 can be left on the same tape that is then read by Turing machine 3. And so that's the kind of crux behind why these machines can kind of trivially be composed together. You can always just sort of pass that information or the input after it's processed to the next machine, and because there's no special format that the input has to be in, you can sort of share a tape alphabet across multiple machines and have those multiple machines understand each other's input and output. I said I wasn't going to belabor the point. I kind of did. Apologies. That's just sort of the long and short of section 9.2. So the much more interesting thing is called Turing Thesis, and that is in section 9.3. And so what we're going to talk about now is the kind of motivation, what it actually says, and then what it actually means as a sort of cap on this entire discussion about Turing machines that we've had over the last two videos. So the Turing Thesis is a much more important result than 9.2, and it's really the thing that we've been driving toward in all of these discussions about Turing machines. So the motivation behind this is that you're very tempted after you find that Turing machines can do something like arithmetic, and Turing machines can be composed to do even more complicated things. You're kind of led to believe that maybe Turing machines can do arbitrarily complex things. So you want to make the claim that effectively a Turing machine can do anything that a Pentium 3 can do, or a Turing machine can do anything that a randomly selected person in America's desktop computer can do. And so effectively what you're trying to argue is that given a Turing machine, you can compute some arbitrary set of computable tasks. So we've shown that we could do some basic arithmetic. Potentially, we could also do symbolic integration. Potentially, we could also do all of these kind of counting problems. And potentially from that, we could build this whole calculus. And indeed, we have built a thing called lambda calculus that Turing machines can actually perform. Lambda calculus is actually an equivalence of Turing machines. And so we have these kind of rigorous ideas of what computability means, and what we want to do is we want to make these mathematically rigorous claims about what we can do in terms of computability with Turing machines. And in order to make that mathematically rigorous claim, what we would need is a definition of what this arbitrary set means, right? Is it 5 tasks? Is it 900 tasks? Is it a countably infinite number or an uncountably infinite number of computable tasks? And what does computable actually mean? Does that mean that I can arrive at a final state? What does it mean about the input that's left on the machine? What does it mean about membership versus transducer problems, et cetera, et cetera? And in addition to that, what you would actually need is, for every one of those computable tasks, you would also need a program that actually demonstrates that there is an algorithm that could be implemented on a Turing machine that solves that specific problem. And so obviously trying to derive these two things is extremely non-trivial. And indeed, it's probably impossible to do because if you think of all the different computable tasks that we have done since the 50s or since the 30s in this case, and if you think about all of the different times people have tried to group computable tasks into groups, if you think about things like Rosetta code that are huge data sets of all of the different types of programs that people have written, we're still not there, right? So you would have to know how to provide an infinite number of examples of algorithms that solve this infinite sized set of problems. And so as we've shown in the last two videos, we can derive these kind of small sets of toy problems. But if we only have a provable Turing's thesis that applies to 7 or 8 or 9 or 10 or 10,000 different computable tasks, the pragmatic or practical power of that thesis is fairly limited. So trying to do so is kind of a fool's folly. And so what we might also be tempted to do is try to show that the Turing's thesis is not true by showing that there is some arbitrarily complicated problem that some Turing machine cannot solve. And so this is where we get into unsolvable problems or yet to be solved problems. But even that doesn't necessarily provide any practical insight into Turing's thesis. What we're showing there is that yes, there could be some esoteric problem that we have not shown an algorithmic solution for, but that doesn't necessarily mean that that same problem can be solved by a digital computer. So it doesn't actually help us show that there is any difference between a theoretical Turing machine and the practical implementation that you're probably watching this video on. So to this point, in either direction, people have tried to beat Turing's thesis to death, and it really hasn't proved to be very fruitful. What has happened is attempting to go down either of these paths, showing that there is a thing that could be computed by a digital computer that can't be computed by a Turing machine or vice versa, has ultimately led us to what we call the Turing's thesis in the mid-1930s. So what is the Turing's thesis? Now that we've kind of provided the motivation. It's effectively a conjecture. It is not a thing that can be rigorously proven or mathematically proven. It is an idea that as of yet has not been disproven. This is something akin to the theory of evolution, or pick your favorite conjecture about astrophysics. There are many of these kind of ideas or hypotheses that give us some empirical information about the state of the world that we live in, that we have maybe lab data or we have empirical evidence that supports these hypotheses, but we don't necessarily have a 4,500 page proof that tells us that it's true under all of these rigorous circumstances or something like that. So now that we've kind of beat it up, let's talk about what it actually is. What does Turing's thesis say? There are two forms of it. The weak form of Turing's thesis says that a Turing machine, or this theoretical concept that we've been talking about for now well over an hour and a half, combined between the two videos, can do anything that you can do on a general purpose digital computer. So there are obviously hand-wavy things in here, like general purpose digital computer. You can replace that with whatever desktop machine from 1997 your grandmother has at her computer desk, something like that. What we're trying to show is that the theory that we are developing in this class is directly transferable to an actual physical machine that somebody can build out of silicon and electricity. The stronger form is effectively an attempt to define what computability is by saying that a thing is computable as long as there exists a Turing machine that can compute it. And so as we go through a more rigorous definition of what computable is or what computability means, and as we go through things like P versus NP, we're going to encounter this idea that in order to show that a thing can be computed, as long as we can whip up a Turing machine, we can show that this strong form of Turing's thesis is effectively using that definition in reverse and saying that a Turing machine can compute something as long as that thing can be computed. So what this leads us to is the fact that Turing's thesis has a lot to do with how you're trying to use it. So the purposes of this class is actually sufficient to start thinking about a Turing machine or an instance of a Turing machine that has a specific configuration of a control unit with an algorithm, right? And so we've talked about how we can use this intermediate state representation to actually infer what the control unit should look like. And so we've already talked about how there's a clear relationship between the algorithm that we're trying to implement and that control unit. And so what we want to do is we want to start talking about that relationship and figure out what the equivalence or what that relationship actually looks like. So definition 9.5 in the text, it's on page 248 of my version of the textbook, gives us exactly the sort of mathematical definition of an algorithm that we need in order to make this relationship as clear as physically possible. And so that definition looks something like this. If I have a function, and that function has some domain and some range, we say that there's an algorithm for that function, and that algorithm is equivalent to a Turing machine if that Turing machine can take some element d inside of our domain, so this is just some string input, and it will eventually halt. So remember the difference between an acceptor and a determiner, or a machine that actually determines a language. It has to stop, so it has to either definitively reject or accept with the correct element of the range that is mapped to that element of the domain on the tape after the machine has done its job. So what this little math bit here is saying is that I can start with some Q0, and the tape can originally have some element of my domain, so some input string on it. After some number of steps, so the Clayton star, of configurations of my machine M, I'm ultimately going to end in some final state that is followed by the range element that is mapped to that element of the domain. And so remember, in our previous examples, we have left QF at the end. Doesn't actually matter. You can take QF and rewind it to the beginning. It's kind of inconsequential. What this is saying is I can take an element of the domain to begin with, I can translate it into an element of the range, and I can terminate in some Q sub f such that Q sub f is in our final accepting states, and this is true for any d that's inside of the domain that I can come up with. So what that means is that this is not only a function that takes some domain element and maps it to the range, it's also a complete function. So there doesn't exist some element of d that I can't derive the correct mapped range value for. So that kind of concludes our fairly long-winded mathematical discussion of what a Turing machine is and is not. I hope that this kind of it was helpful, but I also hope that the previous video sort of helped shed some light on the motivation behind some of the stuff, so that we weren't kind of wading through math the whole time. So again, next week we'll start having online office hours where you can sort of dial into a Zoom conference and sort of ask me questions as they come up. But please, if you have questions, please feel free to email me whatever those questions might be. And I'm currently working at about a 24-hour turnaround on those, recognizing that there's a lot more email traffic now that we're online. So with that, I'll end the video. But again, please let me know if you have any questions, and I hope that things are going well. Thanks.